Hello everyone, welcome back to our videos about reinforced concrete design using the bridge standard BS8110. In this video I'm going to talk about two-way solid slabs, and this will be part number one. It will be introduction about two-way solid slabs, and it will include all the information you need from the BS code to make your design. And part number two and part number three, it will be like two design examples about two-way solid slabs with similarly supported and restrained two-way solid slabs. As you know, in two-way solid slabs, we have a slab supported by 4 beams. And to classify this as a two-way slab, the ratio between the long span divided by the short span should be less than or equals to 2. If the ratio between long span divided by the short span is greater than 2, it means this is not a two-way slab and will be designed as one-way slab. And we have some videos about this. You'll find them. Okay, so if the long span divided the short span is less than or equals to, this is a two-way slab. And as you know, in two-way slabs, we have to design it in both directions because the loads will be going in the short direction, and also we have some of the loads will be going to the long direction. And to make our design, we have to design the slabs in both directions. Okay, how to do that? We take a strip of 1 meter of the slab in the short direction and also in the long direction. Okay, and then through this strip, we have to calculate the bending moment, and then we design for the reinforcement in the short span. Then we have to repeat again this one, but it will be in the long span. We also get the bending moment in the long span, and once you have the bending moment, you will be able to make your design and get the reinforcement in the long direction. So in the two-way slabs, we have reinforcement in the short direction and in the long direction, and both of them are designed using bending moment values. Okay. So in two-way slabs, we have two main types. The first one is called simply supported two-way slabs and restrained two-way slabs. In the simply supported two-way slabs, the corners are not restrained against lifting. Like, okay, like to show this, if you have a slab, the slab in this case is supported on beams, but there is no connection between the slab and the beams. Okay, so the beams were cast first, for example, and then you have the slabs, we cast it later above the beams, but there is no connection between the slab and the beam. Once you have a slab like this, if you apply a load, the corners here will try to lift up, it will go up. And because there is no continuity between the slab and the beams, nothing will prevent them from lifting up. In this case, we call this is simply supported. Okay. In the second case, when we are talking about restraint, corners are prevented from lifting up. So in this case, the slabs and the beams are cast together. So there is continuity between the slab and the beam. The slab cannot leave the beam and go up. In this case, if you applied a load here, these corners cannot lift up because it will be prevented and will be restrained by the beams. In this case of the slabs, of course, you will expect that you will have some torsional stresses here and this will require additional reinforcement, as we are going to see during our video. Okay, so the question now is how to calculate the bending moment in short direction and also in the long direction. To do that, we have to use some coefficients from the bridge standard BS8110, but these coefficients are not similar to the coefficients that we used in the one-way solid slabs. Okay, so these coefficients will differ based on the slabs that we have it here. Is it the first type, which is the simply support slabs, or the second one, which was the restrained slab? Okay, in the simply supported slabs, as you can see here, we said the slab will not be connected to the beams, just like supported on the beams. In this case, we can get the moment in the short direction. It will be called as mx. And the mx here, we can get it from equation number 10 in the code, which is alpha sx n lx squared. What is lx? Lx is the short span. N here refers to the total ultimate load on the slab, which sometimes we call it W ultimate, which is 1.4 dead load plus 1.6 live load. And alpha sx is a factor, we will get it like within like few seconds from now. Then this is the moment in the short direction, and this is how it will look like, because you don't have a moment here at the end because it is not continuous. Then you have to get the moment also in the long direction. We call it my. My here refers to the moment in the long direction, not the y-axis or x-axis. X here refers to the short direction, y refers to the long direction. So how about this my? We can get it from equation 11. In this equation 11, my equals alpha sy n lx square. So the difference between equation 10 and 11 is only in this first factor, alpha sx and alpha sy. Keep in mind that the lx here and lx here is still the short. So even if you're calculating the moment in the short direction or in the long direction, both of them are depending on lx, the lx, not ly. Okay, so nlx square is the same, but here to get the moment in the x, we use alpha sx. To get the moment in the long direction, which is referred to, we refer to long direction by y, so my equals alpha sy. So what is this alpha sx and alpha sy? These are factors, we get them from the code, and it is exactly from table 313 in page 220. Okay, what do we have here in this page? We have the two equations, equation 10 and 11, and we have this table 313. What do we have in this table 313? The first row here is the ratio between ly and lx. And you can see this ratio, it changes from 1 until 2. Okay, 1 if you have the slab is a square slab, it means ly and lx are exactly equal, so the ratio will be 1. And the maximum ratio that you have it here between ly and lx is 2, because if you exceed it 2, it means it will be a one-way slab, and we have to solve it using the one-way slab method only in the short direction, and we use minimum reinforcement in the long direction. But here, the ratio, it ranges from 1 until 2. Based on this ratio here, you will have the coefficient, which is alpha sx and alpha sy in the second and the third row here. So let's, for example, if you have the ly over lx equals 1.2, in this case, alpha sx equals 0.084, alpha sy 0.059. You just substitute these values into these two equations, 10 and 11. You get the moment in the short direction, the moment in the long direction. And once you have the moment, you can make your design using the regular equations, calculating K, calculating Z, calculating the area steel. Okay, if one will ask, okay, if the ly over lx is not exactly like 1.1 or 1.2, it's something in between. It is 1.23, 1.25, so you cannot get it directly from the table. In this case, you have two options. The first one, you can just use the equation here, equation 12, equation 13. Substituting the value of lx and ly into the equation, you will be able to get alpha sx and alpha sy an exact value. Another method, you can get it by interpolation between, if you have a value here in between, you can make interpolation between the values before and after, and in this case, you will be able to get the value of alpha sx and alpha sy and substitute into equation 10 and 11. Okay, this is the first type, which is simply supported. We have two moments, positive moment in the short, positive moment in the long. How about the second type, which is restrained slabs? In restrained slabs, we have more moments. Okay, as you can hear, we have 6 different types of moments here. 2 moments will be like positive moment, similar to the simply supported one, but with different values, of course. And then we have some negative moments at the edges, M1, M2, M3, and M4. Okay, so we can classify this into some moments in the short direction and some moments in the long direction. In the short direction here, we have a positive moment at the mid-span, which is called MX, this one, MX. And then negative moments, it will be at the support, will be M3 and M4. So MX, M3, and M4, these are moments in the short direction. Similar to these ones, we have also moment in the long direction. Positive moment will be called My here, and then some 2 negative moments about the 2 edges, M1 and M2. How can we get these 6 moments? Okay, we can do that using equations 14 and equation 15. In equation 14 and 15, they are very similar to equation 10 and 11 in the case of simply supported, but the only difference here, instead of alpha sx and alpha sy in equation 10 and 11, here in this equation 14 and 15, we have beta sx and also beta sy. Okay. NLX square, NLX square is exactly similar to equation 10 and 11. So what is beta Sx and beta Sy? These are coefficients. Again, from the code, we get them from table 314 and page 221. Let's go and see what do we have here in this table 314. In this table 314, you can find this is bending moment coefficients for rectangular panel supported on 4 sides. So these are our panels, two-way slabs and restrained because we have some torsions, stresses, torsion moments at the corners. So these are restrained slabs, and we have different values. We have many values. This is not similar to table 313 in the case of simply supported. In case of restrained, we have many different cases here. Like interior panels, one short edge discontinuous. And to be able to see this, we have like a drawing here. This is showing a plan in a building. Each line here refers to a beam, and we have different slabs. So the first case, if you have interior panel, what does it mean interior panel? Interior panel, it means you have continuity in all directions. Yeah, it means here, if you have a slab like this one, this slab is continuous from this side, for other side, this is the third and fourth. So from all 4 sides of the slab, it's continuous. So we can call this as interior panel. So if you have an interior panel like this, the values of beta Sx and beta Sy you can get from the first part here, this part, okay? Then if you have a second case, one short edge discontinuous, okay? For these slabs here, like if we have a slab here, this will be the long edge, this will be the short edge. So where is the second case? One short edge discontinuous, okay. Here, okay, this one is one long edge discontinuous, and here one short edge discontinuous. We cannot see this case. I cannot see this case. Okay, if we have discontinuous, no, I cannot see this case here. One short edge discontinuous. It is not here, but let's see the other one long edge discontinuous. Yani only one long edge discontinuous, which is this case here. Okay, you have a slab which is continuous from 4 sides, 1, 2, 3, 3 sides continuous, and one edge here is discontinuous, which is the long edge. So one long edge discontinuous, it will be this case. Then 2 adjacent edges discontinuous. Okay, like this case here, you have two adjacent edges discontinuous. The other 2 edges are continuous. 2 short edges discontinuous. Okay, 2 short edges discontinuous, like a case here when you have this short edge discontinuous, but even the fourth one, the third one is discontinuous. So you may have different cases based on your plan, based on the slabs that you have, if interior panel or one short edge discontinuous or one long edge is discontinuous or 2 adjacent edges continuous and so on. Even like you have other cases which is not included into this slide here, but you can see it in the table 314. Okay, so once you defined your slab and you choose the best one here, which is will be similar to the slab you are solving, so the suitable one, then you have to get the values. So the first step, choose the right one here. Okay, so if I'm dealing with this slab here, this slab is inferior because continuous from all 4 sides. So I'm going to choose the values from here. Okay, you choose the values here, but which values you are going to use? Then here, short span, and then you have for long span. For the short span, you have different values of this beta Sx. Okay, based on the ratio between Ly over Lx. So if Ly over Lx, you can see here it changed from 1 until 2. Based on the value here, if the value, for example, 1.5, so the beta Sx equals, you have 2 values. One value for negative moment at the continuous edge, and for the positive moment. You have one value for the positive moment at the mid-span. It will be this value here. Beta Sx positive is 0.040. And then beta Sx, but at the negative, at the edges, it will be this value, 0.053. Okay. How about the long direction? The long direction, it is not depending on the ratio between Ly over Lx. It's constant values, one for negative moment and one for positive moment. Okay. So again, let's go to if you have a case like this one. Okay, this one here. It is two adjacent edges discontinuous. Okay, so where is two adjacent edges discontinuous? It is this one. What is the ratio between Ly over Lx? Whatever the ratio here, let's say, assume it is 1.2. So for the short direction, short span, and then these values will be for the long span. The first value here will be for negative moment in the short span, then positive moment in the short span. Then in the long direction, you will have negative moment and then again positive moment. Okay, and this you can apply this to any type of slabs. You have it here based on which panel you are solving. Okay. So this is how to use table 314. It will be very clear when we solve examples together in the coming videos. Okay, the values that we calculated based on the previous tables in the two-way slabs, we can use them to design only the middle strip. Middle strip in the short direction, middle strip in the long direction. What is this middle strip? It is 3/4, 3/4 of the span. Okay, so the short direction here, the moment that we calculate, we can use it to design for this strip. How about these ends? The 1/8 end here, the 1/8 end here, we can use only minimum reinforcement. Okay, the same for the long direction. The moments that we get for the long direction, we design for the long direction, but for only middle strip. For the outer strips here or edge strip, we can use the minimum. But in practice, the values of the moments that we get from the previous tables, we just use it to design for the short direction, all the short direction from the beginning to the end, and also for the long direction here, from the beginning to the end, the whole width of the long direction. Okay, but according to the code, it allows you to do that. But in practical, we just design for the whole width of the slab. How about shear forces? Also shear forces in the two-way slabs, we can determine them from equation 19 and 20, which these equations are very similar to the equation 10, 11, or 14, 15 for the bending moment. But we have some difference here. The shear in the short direction and the shear in the long direction, we can get from this equation, beta Vx n Lx, beta Vy n Lx also. Here, the difference between these two equations, a previous equation for the moment, n is the same, but here the Lx and Lx, it's not a square. In the case of the moment, we use Lx square, beta alpha Sx or beta Sx n Lx square, but here in the shear, we use only Lx, not a square. And the coefficient here, instead of alpha and beta Sx, alpha Sx and beta Sx, in case of moment, here we have beta Vx, beta Vy, and as you know, V is always referred to shear. Okay, so how to find this beta Vx and beta Vy? We have table 315 in the British standard, like this page 223, and you can see here again, similar to the case of restrained slabs in a case of a moment, it is also similar based on our edges, 4 edges continuous or 1 short edge discontinuous, 1 long edge discontinuous, and you have different cases also. And based on that, we have beta Vx and beta Vy. Beta Vy, it means the coefficient in the long direction, and beta Vx will give you the coefficient in the short direction. And in the short direction, it depends again on Ly over Lx. You can go here and you get only one value directly, because this is not a moment, negative moment and positive moment. It is only a shear, and the shear will be at close to the edges, and the value here, you get it in the short direction, and this is the value in the long direction. Okay. You have sometimes cases when you have continuous edge or discontinuous edge, and values in case of continuous or discontinuous also. Okay. But like keeping your mind in the shear, if you are designing slabs or like a floor with different slabs, you need only to check a shear one time, because if the shear, like take the critical shear, the value of the maximum shear, and check this value. If the shear is safe, it means at any lower values, the shear also will be safe. For the moment, you have to design at different places, because each moment will give you a different value of reinforcement, tensile reinforcement, and you will have different values of reinforcement at different places or at different position of bending moment. Okay, so this table 315, we can use it to get the shear values, and as I told you, we check for the maximum shear, and then if it is safe, all other values will be also safe. Just we have an important note here that the British standard is not allowing to use shear reinforcement in a case of a thickness less than 200 millimeters. So if the thickness of the slab, the H, the total height of the slab is less than 200 millimeters, you are not allowed by the code to use shear reinforcement. So if the shear is not safe and the thickness of the slab is less than 200, what is the solution? The solution is to increase the thickness of the slab. Okay, in a case if you have a slab of greater than 200 millimeter, let's say 250 millimeter thickness, and the shear is not safe. So in this case, you have two options. You can use shear reinforcement, or you can just increase the thickness of the slab, which is the easier way. Okay. And also, of course, as you know, the shear, you can calculate the shear based on the table 316, the regular shear if the V is less than VC, so nothing is required, no links are required. If the V is greater than VC plus 0.4, it is minimum links, and if it is greater than VC plus 0.4, of course, you will need to design for links. But also, again, just in most cases, when we are talking about solid slabs, in 99% of the cases, you will find that the shear will be safe, and you will be within the first case here that V will be always less than VC, and in this case, you don't need shear reinforcement. Okay. How about torsional reinforcement in restrained slabs? As I told you in the first or at the beginning of this video, in the restrained slabs, the corners here wants to go up, to lift up, but because of this continuity between the slab and the beams, they are restrained. They cannot go up, and you will have some torsional stresses at these corners here. These torsional forces, torsional stress will require to have some additional reinforcement to resist for these torsional moments. And in this case, we have three different types of corners. Corner number 1, corner number 2, and corner number 3. In corner number 1 here, we can see that it is not continuous in both sides. It means like this is a corner, an end corner of the building, not continuous from this side, not continuous from this side, and this will be the most critical corner. Another corner here, when it is the slab is continuous from one side and not continuous from the other side, this will be like less important than the first case. And the third case, C3, when you have the slab here is continuous from all sides. Okay, and let's see what the code requirements for each case. At corner number 1, which is the critical case, the slab is discontinuous in both sides, no continuity here, no continuity in the long direction or in the short direction. So the code requires to have torsional reinforcement, and will consist of 4 layers of bars, 2 top and 2 bottom layers. Why 2 top and 2 bottom layers? Because as a top layer, you will have in the short direction and also in the long direction. And similar, you will have 2 layers in the bottom reinforcement, long and short directions. Okay, what is the requirement for that? Each layer placed parallel to the side of the slab with length of greater than the span over 5. Okay, it is greater than the LX over 5. So you will have the 2 layers here. The length of these bars that you put here, it will be the span, the short span over 5. 20% of the short span here and 20% of the short span in the other direction also, top and bottom. But what will be the quantity of the reinforcements that I will have here? The area of steel in each layer shall be 75% of the area required for the maximum mid-span moment in the slab. So if you have reinforcement here in the slab, at the middle of the slab, due to positive moment, so the reinforcement that you will have it here for torsion will be 75% of the area required for the positive moment reinforcement. Okay, and the reinforcement in the other direction also will be 75% of the reinforcement in the other direction. Okay, this is in case of corner number 1. In case of corner number 2, it will be half of the corner number 1. You will need only torsional reinforcement in the discontinuous direction. So it will be here. Again, it will be, the length will be 20% or short span over 5. And you will have top layer and you will have bottom layer. You don't need, in this case, reinforcement in the short direction because of continuity. The Third case at corner number 3, because it is continuous from all sides, no torsional reinforcement is needed because the torsional stress will eliminate each other here at this corner. So the most critical corner, it is the corner when you don't have any continuity in both directions, followed by the case when you have continuity in one direction and discontinuous from the other direction. And the last case, which is C3, in this case does not require any torsional reinforcement when it's continuous from all sides. Okay, now we'll go to the design steps of two-way solid slabs according to the BS code. The first thing that keep in mind that we always design the slab as a beam with a width of 1 meter. So always the B, the width of the section will be 1000 millimeter. Okay, and you will see that in most of these cases, it's the repetition of what we have taken in the one-way design steps videos. You can go back and check the videos. So after considering 1 meter, we have to start by the initial proportioning. In the initial proportioning, we get the slab thickness. We call it H or HF. And to do that, we have to use table 3.9, page 215. And I go back here. This is table 3.9. We have a basic span to depth ratio. Based on the case that you have, if it is simply supported, the basic span to depth ratio will be 20. If it's continuous, the basic span to depth ratio will be 26. Okay, and we'll use the same equation we used in the previous video about one-way slab, which is once you have this value, you will be able to get the minimum effective depth equals the span divided by the basic ratio, which we get it from this table here, but multiplied by a modification factor. And as a guide, we can assume this modification factor as 1.3. Okay, this is about calculating the depth. Then you need to get the cover. Okay, what is the cover here? The cover is the larger from two values, durability, table 3.3. It depends on what is the type condition of exposure, mild, moderate, severe exposure. And based on this, you will be able to get your cover. And again, the second one about the fire resistance from table 3.4, and this is table 3.4, based on how many hours you want your structure to resist the fire, and this is depending on the fire resistance per hour, and also depends on the type of the structure or the structural element you are designing. If it is beam, if they are talking about floors, and floors include simply supported, continuous, and also cantilevers will be assumed like as a simply supported. Then if you have some reps, and also for in a case of the column, you can, once you have the value here, and based on if you are designing a beam and 1 hour, it will be like 20 and so on. Okay, this is similar to what we did in the one-way slabs. Once you got the D and you got the cover, you take the maximum of the two, the larger of the two values here, and then you will be able to get the total H equals D plus cover plus phi over 2, which is the diameter over 2. And as a guide for the diameter, we can assume it as 10 millimeters. So the total H will be D from table 3.9 plus cover, which is the larger from table 3.3 plus 3 and 3.4, plus the diameter over 2. And the diameter is always assumed as 10 millimeters. So this value will be always as 5. So this is the first step, initial proportioning. Once you have the thickness, the H of the slab, you will be able to move to the second or the third step, which is the final proportion. And it is the ultimate limit state and will include calculating the loading. Loading will include dead loads, which will be like the self weight of the structure, weight of finishes, weight of partitions, if you have ceilings, surfaces, and so on. In addition to that, you have also the live load, which is taken from the BS8399 part 1 code and depends on the function of the building. Once you have the dead load and you have the live load, you will be able to get the N or W ultimate, which is 1.4 dead load plus 1.6 live load. Once I have the N, I will be able to go to the structural analysis step and to get the bending moment. As you know, the bending moment, we can get it from table 3.13 in a case of simply supported from equation 10 and 11. Okay, this is the N, this is Lx, and this is the table 3.13 to get alpha Sx and alpha Sy. Or in a case of restrained, you can get it from table 3.14, which is this table here, and depends on your panel interior or one short edge, one long edge, discontinuous, or two adjacent edges, and so on. Based on that, you will be able to get the factors of alpha beta sx and beta sy. And in this case, don't forget that you will have negative moment, and also you will have positive moment in the short direction, and similar negative moment and positive moment in the long direction. Okay. Also, you can get the shear force from table 315 that we just finished, we saw in the previous slide. No need to go back to see this table. Okay, once you got the bending moment and the shear force, you can start making your design. So you design for reinforcement. As usual, we calculate the K, which is equal M ultimate divided by FCU BT square. Once you calculate the K, calculate the Z, and just keep in mind that the Z will not be taken as greater than 0.95D. If it is greater than 0.95D, just take it as 0.95D. Then we calculate AS required, which is the M ultimate divided by 0.95 F yield times Z. Once you have the AS required, you will be able to choose the diameter and the spacing. From where we choose the diameter and the spacing, we have a table here. I don't know if why it is not working. Okay. Later on, we'll see about this table. There is a table that will help you to find the, once you choose the diameter, it will give you the spacing of the bars and also the AS provided. Okay, so you got the AS provided, you choose your bars. You have to make your checks about checking for deflection, which is table 310. Okay, calculating M factor from equation 7 here, which depends on Fs, the stress in the steel reinforcement, which you can get it from equation 8. The stress in the reinforcement equals 2 over 3 F yield, AS required divided by AS provided, times 1 over beta B, and always we assume beta B as 1. Once you have the Fs, you just take it and put it into this equation with M over BD square. And keep in mind that the M here is the maximum positive moment. So we check the deflection at the maximum positive moment. Then you check the deflection, and if it is safe, you have to check the shear, and then check for cracking. And for cracking, we have two checks we have to do. The first one about the minimum percentage of reinforcement. Your reinforcement ratio should be greater than this minimum. For the slab, the minimum ratio is 0.13% of the area of the concrete, similar to what we did in the one-way. Nothing differs from the one-way solid slabs. And then also for section 3, 12, 11 to 7 about the spacing, and it tells you the maximum spacing that you cannot exceed is the lesser of 3 times the effective depth, or 750 millimeter. I'm going through this very fast because we already discussed this in our previous videos about the one-way slabs. Once you check the cracking, it's fine. Then you can make your drawing and checking for detailing. And for detailing, we have figure 325, but this is a simplified one. The one in the code is more complicated. You can see it in our videos of one way, but this simplification, it will give you that you can cut some of the bars, 40%, 60% of the bars you can cut them, 40% can be continuous, and the same in case of continuous continuous slabs. Also 40% will be continuous, 60% you can cut, and also for the negative moment. So it is exactly similar to what we did in the case of one-way slabs. Okay, this is the end of our lecture. Thank you, and let's meet again in designing part number 2 about designing an example of two-way slabs, simply supported two-way slabs, and then we will go to part number 3 about designing of two-way restrained slab. Thank you, and see you again in a coming video. Goodbye.